Great. So, hi everyone. Hope you enjoyed lunch. So we're starting the afternoon session with Santhoshini. We'll talk about optimal algorithms for detecting heavy hitters in random module streams.
Thanks, Talia. Good afternoon, everyone. Hope we don't put you to sleep. I mean, I'm sure you're all full after lunch. But thanks to the organizers for inviting me. Today I'll be talking about a joint work with Hua Cheng Yu on designing optimal algorithms for detecting some objects called heavy hitters in random order streams. Alright, so what are these heavy hitters? These are elements that typically occur most frequently in a stream. Such elements could be really useful to detect in like practical settings where you're, let's say, monitoring network traffic, or you want to identify, you look at stock data and want to identify which stocks are traded the most, things like that. So they have lots of applications in real world, and also in theory, the heavy hitters algorithms have been like used as subroutine in several algorithms, like norm estimation, entropy estimation, and lots of other algorithms. So these objects are really well studied in the literature. Here's a formal setup. So you have a stream of n elements, A1 to AN. We assume that they come from some universe of poly n size. So that means that every element has a log n size representation. Okay. Now, the stream itself can be represented as a frequency vector, where f sub I just denotes the frequency of element I in this stream. Okay. Now, there are multiple ways in which you can define what a heavy hitter is, and here I will define a couple of guarantees. First is the straightforward L1 guarantee. It says that, say I fix some parameter delta, then I want to output every element that occurs in at least delta fraction of the stream. Stream length is n, I want to output every element that's at least has a frequency of delta n, and I don't want to output any element that's like below half this threshold. And the second guarantee, which is a little bit more involved, is the L2 guarantee. In this, we consider the sum of frequency square of the elements, or in other words, like the L2 norm square. And then we say that you want to output an element if its frequency square is at least delta fraction of F2, and you don't want to output anything that's below half the threshold. Now, if you notice, the second guarantee that I mentioned is actually a stronger guarantee than the first guarantee in the following sense. Let's assume delta is a constant. And let's say that we have a stream where F2 is order n. Now, if you look at the first guarantee, what it's asking you to do is like output an element that occurs in at least constant fraction of the stream. And while the second guarantee, it says that Fi square is at least delta of n, which means that the frequency itself is only like square root of n. So for the same like constant factor, L2 guarantee asks you to find an element which occurs in a negligible portion of the stream. It has a frequency only square root of n when the length of the stream itself is n, but the first guarantee you're asking to find something that occurs in like constant fraction of the stream. So in that sense, like L2 guarantee is typically harder to achieve compared to the L1 guarantee. Does that make sense? And for the purpose of this talk, I'm going to be focusing on the L2 guarantee. Great. So this is the classical algorithm to solve this L2 guarantee. This is a count sketch algorithm due to Cherikar, Chen, and Martin Farah-Holton. And they managed to achieve this L2 guarantee in log square n over delta space. And this actually turns out to be optimal for turnstile streams. Basically streams where you also allow deletions along with insertions of elements. Now, so it's natural to ask, can we do anything better in insertion-only streams? So this amazing paper due to Braverman, Chestnut, Ivkin, Nelson, Wong, and Woodruff show that, in fact, you can shave the log n factor from count sketch. So count sketch use space log square n over delta. Now, if you just consider constant delta, then they are able to achieve L2 guarantee in order log n space, which is optimal because even to represent your element, you need log n space. So might as well just like outputting the element is all the space they need, even to like run the entire algorithm. Now, so this is true. If it's constant delta, they'll achieve optimal space. But if delta is not constant, there is a gap between the upper and lower bound. So the lower bound is just that. So if you're looking at delta heavy hitters, in the worst case, you can have 1 over delta many heavy hitters, so you need 1 over delta times log n space. And the space they use is like 1 over delta log 1 over delta log n space. Oh, yes.
Do we have any results that like with high probability? Because I think in streaming you can't repeat it many times to change a constant probability to with high probability.
Some sense, okay, very good point. So I think their result is, okay, yes, they have a high probability result, but somehow it appears in the space also. So you could, I think, run like parallel executions of the same algorithm, and in some sense still you can boost
Oh,
it.
I see. Yeah.
So you could still do that, but you would have to pay for it in space.
Right.
Perfect. All right, so that sort of is the goal of us, like can we close the gap for insertion-only streams? And what we managed to do...
The gap is a multiplicative log 1 over delta factor?
Exactly. The gap is a multiplicative log 1 over delta factor, and that's what we're trying to shape. And we managed to do that for random order streams. And we also have a partial... So, okay, maybe I should define random order stream before I move on. Basically, random order streams are streams where an adversary can choose the stream elements, but just the order in which the elements appear are random. And so for these kind of random order streams, we show that in fact it is possible to shave this additional log 1 over delta factor, but not for all range of delta. We're able to show that for like delta, which is at least like 1 over 2 raised to square root of log n. I mean, it sounds like a weird number, but basically we get it because like our algorithm works in some sense for every delta, but the probability that we get is like a function of delta, and we get constant probability only when delta is at least this much. So, which is something we will see soon, but anyhow. We also have, our original goal was to attack insertion-only streams. What we got was random order streams. We tried to see if we could do something beyond random order streams. And we do have like a result for, so what we call partially ordered streams, or partially random order streams. These are streams where you can imagine like, even like stochastic settings, like network settings or something, where maybe your heavy hitter itself is stochastic, so that occurs in random portions of the stream, but the non-heavy elements could be just noise, some adversary places. So yeah, consider such a setting where the non-heavy elements can be adversarially placed throughout the stream, but the heavy element is like random ordered. In this setting also we get the same guarantee as above, but with the caveat that we need to know the F2 or the L2 norm of the stream in advance. Somehow our algorithm relies on the fact that this is known, and so that's what. Any questions about the results? Yes.
So for like the strict turnstile model where you don't let the frequency go to below 0, what does it mean to have a random order?
I actually don't know. So insertion-only streams, I think, is where random order is defined.
I see. Okay.
For deletions, if you have any kind of deletion, like what if you end up deleting something before it was even added?
Oh, sorry. So this, for instance, sorry.
Sorry. It's all only insertion-only streams. So turnstile model count sketch is optimal.
Okay, I see.
And that nothing can be done. Good question about strict turnstile. I don't know if the lower bound also extends to strict turnstile. I think it's for turnstile, but yeah, that's a good question. But yeah, the whole focus is like whether for insertion only can we do better. Yeah, great question. Okay, perfect. So this is going to be the rough outline for the talk. I'll start with a model problem, give some intuition for the algorithm and analysis using this model problem. And then I'll show you how to remove these assumptions that we make in this model problem, and then finally give you some open problems in this area. Okay, first for the model problem, let's assume delta is a constant. And large enough constant so that we just have one heavy hitter, X star. And we're just going to try and find this heavy hitter, X star. Next, we'll make another assumption. Let's say that the F2, or the sum of frequency square, is order n. I've just given some specific numbers here, but the numbers don't matter, it's just for illustration. The point is that, so F2 is order n, and if you look at like the sum of squares of the other elements that are not heavy, that is at most the heavy hitter's frequency square over 3. So it's like a constant factor bounded away from the heavy hitter's frequency square. Okay. The next assumption that I'm going to make is that X star is evenly distributed in the stream. So, we roughly expect, like, if you have a random order stream, then the distance between, or like any two consecutive X stars are going to have like roughly the same distance. Here, let's assume that it's sort of exactly the same. So let's say I have the frequency is at least square root of 12 and whatever here. Then I divide the stream into like equal sized windows of size square root of 12 n. Then there is at least one occurrence of x star in every such window. So imagine like I have a stream, I have divided it into windows. Heavy hitter occurs in each window. Now I'm going to try and detect this heavy hitter. And finally, I want to make another assumption. The length of the stream and F2, they are both known in advance. So I've made a bunch of assumptions. I'm going to use these assumptions and build an algorithm for it. Later, I'll show you how to remove all these assumptions. Okay. So now our goal is actually to output the heavy hitter with high probability using order log n space. That's what we're going to do. Here's just a pictorial representation in case the things that I said before were not clear. So let's say this is the stream of elements. The blue element here is the heavy hitter. And heavy hitter has frequency like order square root of n. If we divide the stream into windows of length order square root of n, there is one heavy hitter in each window. Okay? And any other element, let's say, has frequency at most like square root of n over 100 or something like that. So some constant factor bounded away from heavy hitter's frequency. Now we want to output x star correctly with some hypothesis.
So should we think of it as like sort of the only property of the randomness of the stream that you need is this like spreadness?
Spreadness,
Yeah.
exactly. And spreadness of just the heavy hitter. We don't care about even the other elements, yeah. Perfect, yeah. And so this is sort of like a bird's eye view of what our main algorithm does. And in terms of like the properties of the algorithm, I want to say like what are our desired properties. The first property we're actually going to need is like, let's say it just succeeds with constant probability. So we're going to first design an algorithm that succeeds with constant probability. But it has this interesting property about space where there's only like a tiny fraction of the stream where the algorithm actually uses log n space. So most of the time, like where it's marked in white, is like the algorithm uses log n space. And there is this tiny portion where it uses log n space. And then our idea is that we can boost the success probability by running several parallel executions. We're just going to make sure that because any one algorithm uses log n space in a very tiny fraction of the time, not too many of them, like maybe 10 of them use log n space at a time. So overall, nobody uses more than log n space. Or overall, the space usage is not log n space. Yes.
Do you ever consider like if they use log n space at the same time, or like do you not care about that?
We do care about it, but I'm not going to give like a how do I say it? It's like a black box thing. Like pick any algorithm, I'll tell you how to do this. But it's going to be like we have to work with the dependencies and stuff for our specific algorithm. But we're going to ensure that more than let's say 10 algorithms never use log n space. So mostly all of them use log n space. So we can run like log n over log n parallel executions. So as long as they're just using log n space, the overall space usage will be log n. And the point where anyone is using log n space, at most like 9 other algorithms are using log n space. So overall space usage is going to be log n space, and output is just going to be finally the majority answer. Whichever element is picked the most is going to be a heavy hitter. And success probability, I mean, if they're all truly independent, then you should expect 1 minus 2 to the minus, log n over log n kind of success probability. Of course, this creates some dependencies with the space thing, but that still can be handled and we get the success probability. Anyhow, for the purpose of this talk, I'm only going to focus on the basic algorithm because that has the most intuition that we want to understand what we want. As I mentioned before, so the properties we are going to target are, we want constant success probability, and we want the space usage to be log n only for a tiny fraction of the time. Everything else is going to be log n. So you might wonder, like each entry itself is like, I mean, to read it, you have log n space, then what do I mean by it? So you can imagine that reading an element is free, but you're just charged to remember it. This is because like all the multiple parallel executions can read at the same time. So you don't have to charge it individually for everybody. So that's just overall log n space. You can also get a counter for free because again, you just need log n space overall for all the algorithms, and you can know precisely like the index of your current position in the string. So we'll make a couple of assumptions. Does that make sense to everybody? Okay, perfect. So let's start with some high-level intuition. I'm going to make one more assumption, just so that life gets simpler. Let's say that every other element occurs just exactly once in the stream. So in this example, like all the other colors are just there once. Blue is the only thing that appears more than once. There is a natural algorithm here. You can just sample and check. So sample a random element in every window. Check if that element occurs in the next window. Why would we get a constant success probability here? That was not going to happen. Anyhow, so first of all, only the heavy hitter you can ever output just the heavy hitter, because by assumption, everybody else occurs just once. So if you sample them, they're not going to be present in the subsequent window. But why would we output the heavy hitter or the blue element with constant probability? Each window has like square root of n elements. So the probability that you sample the heavy hitter is like 1 over square root of n. You have square root of n many windows, so constant probability you're going to sample the heavy hitter. Once the heavy hitter is sampled, of course you're going to output it because it's present in the next window. Can someone tell me what's the issue with such a simple algorithm?
It uses too much memory, to remember what we sampled.
Perfect. You are going to use log n space throughout the stream because you're remembering it and checking, and our goal was to use log n space, limited time. Whenever we have space issues, what do computer scientists go to? Hashing. There we go. Hashing. So say we hash it into like log n, polylog n buckets, like log n to the 100 buckets. So now to remember the hash, you need just log n space. So let's say now my goal is to just output the hash value of the heavy hitter. Let's say with at least like probability half. Why would this be enough? So originally I said just take the, like the majority is what I said for those parallel executions. We can slightly modify it. So instead again you run those parallel executions, but now you can output the element which has the maximum hash hits, like use independent hash functions for all of them, see which element has the maximum hash hits and output it, and you can still get the same success probability. So we can all imagine now that we are just trying to output the hash value with some constant probability. Now, a simple algorithm is like sample a random element, remember only its hash value, and check if the next window has the same hash value. This would utterly fail. Can someone tell me why it would fail?
Because we have too many collisions in buckets.
Exactly. Like there are just log n over 100 buckets. You have square root of n elements in every window. Every hash element is going to be in every window. So I don't even know what I'll output. I'm going to definitely output some garbage, the first thing I sample. So this is not going to work. So what we could do is the following. It's a little bit more sophisticated. So let's say W is the window size, which is square root of n in our case. Q is like the sampling probability, which is 1 over square root of n. Basically, we want to sample a random element. But first we do this kind of sampling. This is actually like a pre-sampling. You can imagine that we have free randomness. So all this sampling is like done even before we see elements in the stream and stuff. Basically, for every window of the stream, we are going to sample a set. And this set is just like from the universe. You sample every element with probability 1 over q, with probability q, or probability 1 over square root of n for the example we are looking at. So if you look at the intersection of this set with the window, that basically is like sampling an element randomly with probability 1 over square root of n. The reason why we have these sets is the following. This is just so that I can it's not just I want to compare the hash value with the next window, I also want to make sure it's the same element that was sampled in the previous window. And this gives me a way of remembering which elements were sampled in the previous window. So that's why I have all these sets like S1 to S4. Those are like random samples from the universe where every element was sampled with probability 1 over square root of n. And then what I do is just consider the elements in the window that belongs to the set. On average, you should expect one element to be in it because sampling probability was 1 over square root of n. Now I'm going to store the hash value of that element. Then I'm going to go to the next window. I look at whichever elements have the same hash value, and then I check if they were sampled in the previous round. So I basically check if that element with the same hash value also belongs to the set that was sampled in the previous window. So let's see an example why this would work. So let's say hash value of this pink element is this faded pink. I'm assuming, okay, in my slide the pinks all look different. But it looks like on the projector they all look the same. So please believe me that this pink and this pink are not the same. Let's go with that. So this pink element over here has the same hash value of this element. But then you can see that this pink is hopefully not the same as this pink. So you will not output pink. So you have to trust me on that. So let's go with the blue element. The blue element was like sampled here. So yeah, I just wanted to show the comparison. The blue element was sampled here. This is the hash value. This blue and this blue are the same. That is a heavy hitter. And you see that, voila, that's the same blue that was sampled in the previous thing. You output blue. And hopefully that's how we can detect our heavy hitter. Yes.
So how do you check if it was sampled?
Oh, good question.
Not
So
remembering it.
we don't have to, so we assume free randomness. So that's a very good question. So all these STs are, all we need to know to get to ST, the sets.
ID.
ID, exactly. So I need to just know T, but that's again a very good point. Here, because every other non-heavy element occurs exactly once, to identify a heavy hitter, I just need to look into the next window. So I just have to, I need the ID of the previous guy, which is fine. I know my ID, just -1 is the previous guy, so you can access. But that's going to be a challenge for the most general case. Very good question.
Sorry, can
Yes.
I clarify this a little bit? So like, do you need to memorize like the set that you sampled from the previous?
So that's it. You assume you have access to free randomness. So assume that all that randomness which determines what the set is already exists. Just to access it, you need
Oh,
the
so
index
so
T.
you can read it.
You can read it. You can read it. So you just need to remember T. So if you know T, you can access it. But as I mentioned earlier, you can imagine that you know exactly which point in the stream you are. You can maintain like a global counter for that.
Okay.
So just to go to the previous window, you just know, I mean, you're at T+1, you know what T is.
Okay.
Yes.
Sorry, this is a really silly question, but how would we say we output the blue element?
Oh, yes.
Yeah.
Very good question. Yeah, okay, yeah, go on. Yeah.
Yeah, I was wondering, like, do we have to remember it until the end of the stream or something? Like,
Good point. So I should have drawn a faded blue there. Let's output the hash
the
value.
hash,
of
okay,
it.
the
Yeah.
hash, okay,
Hash
great,
value.
great.
Very great. Actually, it's a very good question. Yes, we can't remember the element. So that was the point here. Going to only remember the hash value,
Okay.
output the hash value. Finally, from
and then-
all those parallel executions, pick the element which has the maximum match with the hash values.
Oh, okay, thank you.
Perfect question. Thank you. Great. All right. So this, again, we can argue that it has constant success probability, much like previously. And the best thing is it uses log n space only when the heavy hitter is sampled or when you have hash collisions. And this can happen only like 1/k fraction of the time because k was like the number of hash buckets. So k was like log n to the 100. So you're going to use log n space only in that fraction of the stream, and so you're good. We got all the properties that we wanted. Perfect. So this basically solves the problem. Oh, yes.
Sorry, maybe you already answered this and I didn't know. It's like, what happens if so because you're only considering the hash value, what happens if you get a collision? Like two things that were not equal, but they end up having the same hash value.
Perfect. So it is right. You would have lots of collisions, but the point is that when you're looking at, like, let's say, like log n over log n executions, the probability that two elements collide on all those hash values is going to be very small. So that is what saves us. Yeah. So
Right.
you
Are
wouldn't
we-
have yes.
Sorry, are we using different hash functions for each
Yes,
execution?
yes,
Okay,
independent.
okay.
Completely like
Yeah.
all the hash functions, everything are independent. The only way those different executions will be correlated is to make sure you're not using too much space. But other than that, they're all independent. Yeah. Perfect. Thanks. Great question. All right. So hopefully we are convinced that when every other element just occurs once, we're in good shape. So what do we do when elements occur? Oh yes.
Can I ask a very stupid question? So, a log n is a very stupid algorithm is just output a random element of the stream. If it's a heavy hitter, you have like way higher chance of outputting it with constant probability if it's showing up constant probability. like if it's constant fraction of elements in the stream are that element,
Great
is the
question.
point that that uses log space the entire time and this only uses log space some of the time?
It doesn't occur constant fraction of the time. That's the whole point.
Okay.
Because like we're trying the L2 guarantee. L1 guarantee is where it's going to occur in constant fraction of the stream. Here the heavy hitter's frequency is square root of n.
Okay.
So you have square root of n windows. It occurs in each window, but it doesn't occur like it's a very small fraction portion of the stream it's occurring. Good question.
So is that if we're doing L1, you can do this algorithm?
You got me. Like, great question. L1, can I just sample a random element in the stream and maybe
Yeah.
But this has some
How would you test success probability?
Success probability is not going to be sugar, but
Yeah.
I don't know what.
there's a one-sided error somehow with this too, which you couldn't do if you were sampling random elements.
What do you mean by one-sided
I
error?
don't know, like you have some probability of just outputting nothing if you didn't sample the heavy hitter.
Fair enough. Yeah.
I mean, there's the Mischke-Gries algorithm. I think achieves its like there's a deterministic algorithm achieving the space bound for L1.
Good. All right. So let's go on to like more general things. So what if you have like I don't know elements occurring more than once? In this example, like you could have the yellow element, like elements that are locally heavy. Basically, they almost look like the heavy hitter. And so in this case, let's say yellow was sampled here, you're going to output yellow, you're going to output green. It's like basically a whole lot of elements are going to be output by the previous algorithm. And in fact, one thing to notice is that if I end up sampling a yellow element, I need to look into at least like 4 windows to know that it's not the heavy hitter. So in some sense, like when I sample an element of frequency f, you need to look into f plus 1 windows to know that it's not. So sure, naive idea could be like store the hash value, check if every subsequent window has an element with the same hash value. Can anyone see the problem with that? I think it's similar to someone what pointed out before, like you have to remember the t. So the one thing we said is like we want to check if it belongs to the sampled set. So if you're just the subsequent window, you can remember t. But if you're like, you don't even have a bound on the number of windows you're going to check, you have to remember t all this time. That is log n space, and so you're going to use log n space, which is why this is not going to work. So what we do is like, we have some kind of like a hierarchical check structure. So it looks like this tree. It has log n levels. This bottom level here is where all the sampling is done, and subsequent levels are going to do checks. And the way this tree is drawn is the following. So let's say I sample some element here. Then I go to, so they're structured in a way that, first of all, at level L, I have, every node has like 2 to the L windows. And I make sure that the index of the first window is a multiple of 2 to the L. This kind of a structure is so that, let's say I'm at a point where I'm trying to check where this element was sampled from, I can sort of follow this tree structure and figure out what are my leaf nodes and where could the sampling have happened. That is sort of the intuition to define this kind of a structure. And here the structure is just that, so a sampling happens here, and then I go to a check, which is like the parent node that's defined as the node in the next level, whose the starting point is like, is the first thing that occurs after this, wherever you did the sampling. And then if the check passes there, you go to the next node and next higher node and so on. Here is some more detailed example. Let's follow some particular execution path. Say, so first of all, as I mentioned before, sampling is done all in the lower level. It's done in the leaf nodes. And then once you sample, you're going to store the hash value of whatever you sampled. And then you're going to check whether this hash value occurs in all. Your ideal goal is to check if this hash value occurs in every window after that, and somehow it also occurs in a way so that it's from one of the sampled elements. So these are what I would call the check nodes. Now, so what is this? Okay, let me label these check nodes A, B, C in this example. And let's look at all these bottom sampling nodes. S0, S1, S2, S3, these be the sets that were sampled. This was the set that was sampled from the universe with probability Q. Okay, so these are the sets. Now, what is A going to do? A, let's say the check reaches A. It knows that the sampling would have been done either in this window, which has the set S4, or the sampling would have been done in this window, which is the set S5. So it's just going to check if there is an element in the union of these two sets, S4, S5, with the hash value H. That was the hash value that was stored. And we want to make sure that this element occurs at least once in all its windows. This is kind of the goal. And if A passes, then it goes to B, and B is going to have a larger set to check, like S0 to S7. C is going to have even a larger set to check. Just the idea is that if you have something that's not too heavy, those elements are not going to occupy your checks. You're going to figure out very quickly they don't have enough frequency, and you're going to just like terminate the check. And so the overall hope is that you don't use too much space, but we will argue more formally soon. Finally, if all the checks pass, we output the hash element. So this is sort of the high-level idea. I haven't yet even told you what the check procedure is, but hope the high-level idea makes sense. Okay, so what is the check procedure at every node? Pick some node P. And let's say S is the set of elements relevant for the check procedure. When I say set of elements relevant for this check procedure, what I mean by it is it must be the set of all possible elements that were sampled, and these elements should also have hash value H, because you care about only those elements. For example, for node A that we defined previously, these would be elements in the set S4 union S5 whose hash value is H. We just want to check if there is some element there that occurs in all of those windows. Hopefully that is a heavy hitter, but at least that's kind of what we're looking at. Does this make sense? All right. Here's our key observation. If the heavy hitter X star belongs to the set S of relevant elements that we're going to be checking, then it's locally super heavy among these elements, which helps us really figure out what X star is in the space that we want. Super heavy elements, how we define them is just like, these are elements where the delta is at least like 1 minus 1 over polylog n. Or in other words, if you look at all the non-heavy elements, the sum of their frequency square is at most 1 over polylog n factor of the frequency square of the heavy hitter. So it's like really heavy, not just like constant heavy, but like 1 over polylog n heavy. These kind of super heavy elements we can detect efficiently, and that's exactly what the check procedure is going to do. So, okay, so first I'm going to argue why this is the case, why this observation is true. So, sorry for the notations, we're going to have a little bit of notations. So let's say that F, for this node P, FIP denotes just the frequency of element I in that node. Okay. And F2P is just the sum of squares of frequencies for elements in that node with respect to that node. So in some sense, I'm treating just the node itself as a substream and just redefining frequencies, L2 norm, everything just for that substream. Now, first claim is that, so we started with the assumption that for the overall stream, the sum of squares is at most order n. Sum of frequency squares is at most order n. But this also implies that if you look at most nodes, their F2 is going to be linear. So each node, we defined it as 2 to the L windows. Each window has size W. So you have 2 to the L times W elements in each node. My claim here basically says that for most nodes, it is true that, in fact, their sum of squares cannot be more than 2 to the L times W. The reason is actually quite simple. These are all disjoint nodes by definition. The sum of frequency square of them cannot be larger than the total sum of frequency squares of the whole stream itself. And this is at most order n. You have n over 2 to the L times W many nodes. So most of them should have frequency square at most 2 to the L times W. So just like a counting argument. And the second part is that, so now we want to argue that the heavy hitter is super heavy. first, what is the sum of frequency square, or the frequency square of the heavy hitter? The heavy hitter occurs in every window. There are 2 to the L windows. So number of occurrences of the heavy hitter is at least 2 to the L. So frequency square is 4 to the L. What we will show is that the expected frequency square of everything else in the set S, that was relevant set, is at most 4 to the L over K, where K was the number of buckets, which was like super large, like log to 100. So this would show that the heavy hitter is really super heavy among this relevant set we are going to be looking into. That helps us detect the heavy hitter efficiently. Okay, so to argue that this is the case, so first notice that this expectation is basically like you look at the second moment of this node, which is F2P, and multiply it with the probability that an element belongs to this relevant set S. So, and my claim is that this probability is at most 2 to the L over WK. And if this is true, then you just multiply by F2P, which will give you 4 to the L over K, which is the bound we wanted to prove on the non-heavy elements. Okay. Now, to prove that, just notice that, let's say I take a node at level L. How many children can it have? It can have 2 to the L many children. Each child is a sampling node that can contribute to a set S, and all the sampling probability was just Q. So you have 2 to the L sets. Each has sampling probability Q. And after that, you also have this condition that they should have the hash value, which is same as the sampled, like H. Like the set of relevant elements should all have hash value H. And the probability that a sampled element has hash value H is like 1 over K, any fixed hash value. So that's it. So 2 to the L times Q times 1 over K, 2 to the time L over WK. So sorry that it's a little bit technical. If none of this makes sense, don't worry. Just remember that the property that we wanted is that heavy hitter is going to be like super heavy among these set of elements that we're going to look into. And so we want to design an algorithm, like a check procedure for these super heavy elements. And previous slide was just like a justification, if you were interested, for why the heavy hitter is super heavy. That's it. All right, so let's go back to this. So we did this observation. So I'm going to give you an algorithm to detect super heavy elements. And now you can actually forget the entire thing I said. So think about your super heavy element as an element which has a frequency square that's like polylog factor more than the frequency square of everybody else. So if your frequency is like n, everyone else's frequency is going to be like at most n over log n or something. So now in this case, how are we going to detect such an element? So if you're again going to try and naively sample and check, it could take log n space throughout the stream. Because like if the heavy hitter occurs everywhere in the stream, and if you're going to just sample an element and check if it occurs in the whole stream, you could take a lot of space. So the idea is that we are going to sample and check up to only polylog n fraction of the windows at a time. So here I want to make sure like something is clear. So we sort of go between like hash value and actually storing the element like a few times, so it might be a little confusing. In the end, the goal is to output the hash value. But if you it doesn't make sense to just check if the hash value occurs everywhere, because hash value occurs everywhere. So the point is that you're not just checking if a hash value occurs everywhere. You're going to like sort of do this reverse mapping. Okay, I have a hash value. I know a set of elements from which could have been sampled, which have the same hash value. I'm just checking if there is some element in that set that occurs in all the windows that I'm looking at. So I do have to remember the element to make sure that it occurs in like all these windows or something. But I want to make sure that I'm not remembering it like all these windows that I'm actually ending up using log n space. So there is some subtlety here. That's okay. So now my goal is like whenever I'm actually checking an element, I shouldn't be checking like all the windows. Rather, I'm only going to look into like 1 over polylog n fraction of the windows. So let's say, you have like, we are considering a node with 2 to the L windows. So the size of the node or the number of elements is like 2 to the L times W. So I define this quantity which is log of that size. So consider a second sampling that we are going to do, where this sampling is with probability t over 2 to the L. And that means that I'm going to roughly sample the heavy hitter t times in this node, okay? Because the heavy hitter occurs in every window. So now what I'm going to do is like just sample every element with this probability t over 2 to the L. If an element is sampled, I'm going to check the next 1 over polylog n fraction of the windows. K is like some large log n to the 100. So next polylog n windows, I'm going to check if that element actually belongs to the window, if it's present in the window. If a window does not contain it, I basically stop checking for that element and continue sampling other elements. So again, like one thing to notice is that I'm only sampling elements in S. This is the relevant set. I'm only going to check if there is some element in the S that occurs in all the windows. That's my goal. And if all windows that I'm checking contains the element, I'm incrementing a counter. Finally, if the counter value reaches, let's say, t over 4, I say the check passes, else the check fails. This is basically the entire algorithm. Okay. Now, let me show you like why this algorithm is going to be successful. First, I show that the success probability is actually 1 minus exponential minus t, where recall that the sampling rate was t over 2 to the L. This is because the heavy hitter has at least one occurrence in every window. You have 2 to the L occurrences of the heavy hitter. Sampling rate is t over 2 to the L, so in expectation you should see t times. The heavy hitter should be sampled t times. And notice that whenever the heavy hitter is sampled, you're good. It's going to occur in the next whatever number of windows I'm checking, so you're always going to increment the counter that we talked about. So the counter should be incremented at least 2 over 4 times, and we are in good shape. Why is this algorithm using only like log n space? So when the heavy hitter is sampled, each time it's sampled, I'm only checking it for like 2 to the L over some polylog fraction of the windows. Whenever a non-heavy element is sampled, first of all, it is sampled, so this is the sampling rate. This is the frequency of the element in that node. So this is the number of times you would expect the element to be sampled. Anytime an element is sampled, we are only going to look into at most the frequency many windows of, because it won't occur beyond that. So that is, if you just put these two together, sorry about the equations, the first term here is basically like you're counting like the number of windows where you're sampling and checking a heavy hitter. T samples of the heavy hitter, each time it's sampled, 2 to the L over polylog fraction of the windows are going to be checked. T is like log n. T was log 2 to the L times W or something. 2 to the LW is like the length of the node. A length of the node cannot be more than the length of the stream, so it's at most n. So T itself is like log n. So if you look at it, the first term is like 2 to the L over some polylog n. So we are great. Like length, like we didn't want to use log n space for more than polylog n fraction of the stream. So whenever heavy hitter is sampled, that's true. But it's also true for the rest of the elements. This is because, like, again, if you put these two together, it's like this was like the expected number of times you sample it, and this was the number of windows in which you have to look for it. Now, if you put them together, you get the sum of squares of the frequency of the element, which we said was heavy hitter is like super heavy. So the sum of frequency square is at most like 4 to the L over some large polylog n. And so again, it is true that even for the non-heavy elements, you don't expect to use more than polylog n fractions. So the conclusion is that this algorithm succeeds with a high probability, and you ensure that you don't use log n space for more than 1 over polylog n fraction of the time, which was our goal. So that sort of concludes the algorithm. I'll quickly go over how high-level ideas of how we remove the assumptions that I made when I began the talk. The first thing actually is not a very big deal. I assume that delta is a constant and F2 was order n. In fact, all those parameters that I wrote before, like W, window size, Q, sampling probability, hash function, everything can be modified to be functions of this F2 and delta, and we can get the following result. You get this weird looking success probability, which is at least a constant for delta that's in this range, and which is why our result works for delta in that range. Okay? So that assumption is not hard. Second thing, the evenly distributed heavy hitter. So in random order streams, heavy hitter does not quite occur in every window, but it should occur in like every log n windows. So all we do is that in the super heavy hitter algorithm where we are looking at every window for an occurrence, just look into every log n windows for an occurrence, and it basically doesn't change anything. Next, this assumption that the length of the stream is known in advance. Where did we even use this assumption? We used it in setting the window size. So if we know that there are n elements in the stream, and if we know that the F2 is like order n, then we knew that the heavy hitter must have like frequency square root of n, and so we set the window size to be like square root of n. So really the assumption that n and F2 are known, if we just know the window size, if someone can just promise me there is this window size, so that in each window there is an occurrence of heavy hitter, then all I need to know is the window size. So that's where we really use this information that n is known. And, oh yes. Oh, I have fun. Okay, sorry, thought it was a question. Yeah, I'm done. So the point is that our algorithm still works if only we know a constant approximation to n and a constant approximation to F2. So that's what we're going to use to say that, in fact, we can eliminate this assumption that n is known in advance. So the algorithm still works if only a constant approximation to n is known and if it's only executed on a constant fraction of the stream. So our idea is that you basically maintain a constant number of guesses for what n must be. And when you notice that some guess isn't working, you basically eliminate that guess, add a new guess, and start a new execution of the algorithm. The point is, if you maintain, I don't want to go into the math, but if you maintain enough number of guesses, you can show that the point where your correct guess was added, you wouldn't have lost much of the string. Like you would have lost like a tiny fraction of the string, so you're fine. That's sort of the highlight. Next assumption is that F2 is known in advance. This is the hardest assumption to remove. So far, we have only been able to get rid of it for fully random order streams. We were not able to remove it for partial order streams, partial random order streams. Again, as I said before, algorithm still works if you only know a constant approximation to F2 and it's executed on some constant fraction of the stream. Here, our basic ingredient that we use is an F2 tracking algorithm due to the previous paper, the Braverman, Chestnut, Ivkin, Nelson, Wong, and Woodruff paper. This basically guarantees that with at least let's say a constant probability, I can get an additive error to F2 at each time step. So this is like an F2 tracking algorithm that they have, and this algorithm just uses log n space. Now what we do is, again, you can maintain constant number of guesses for F2, and basically, you can do the same argument, but the catch is that you know that at the point where your correct guess was made, the remaining F2 is only a constant fraction of the total F2. But when it's random order streams, if, let's say, you're looking at a point in the stream where the F2 value is the constant fraction of the entire F2 value, the stream length should also be a constant fraction. Because for random order streams, the idea is that the spread is uniform for all elements. The adversary cannot add some bunch of elements at some point that really shoots up F2, and some other point it's spread or something. So we can argue that the length of the stream also was just a small constant fraction, so still you're okay. But that's about it. So summary is that for fully random order streams, we get the best guarantee for delta in this range, and partially random order streams, we can get the guarantee, but we need the additional assumption that we know F2. Open problems are, first, get rid of the assumption that F2 must be known in advance. Can we improve the state-of-the-art algorithm for purely insertion-only streams without any random order assumptions, or can we prove a better lower bound? One other interesting question in the literature, which is very closely related, is basically just L2 norm estimation, or the F2 estimation itself. Currently, there is a gap between F2 estimation between random order streams and insertion-only, just pure insertion-only streams. Is it true that can we do better for random order streams compared to insertion-only streams, or is there some lower bound even for random order streams? So that's it. Thanks a lot for listening.
Any questions?
For the case, so you said for partially random, you need a constant factor approximation to F2.
Yes.
What if you use like previous algorithms to get a log n factor approximation to F2? Because then you can initialize their algorithm with smaller space, right? Because you get slightly, maybe.
Problem with log n factor approximation to F2 is like window size. Like we really need to set the window size. Window size cannot work with a log n factor approximation.
What about log n? I'm gonna keep going until I say it works.
Right now, unfortunately, only works for like constant factor
I see.
approximation.
Should it be 2 pass though, or is it 1 pass?
Oh, you're asking
Or then it would be 2 pass or?
Oh yeah, I guess then it would also be 2 pass. Yeah. Maybe. Yeah. Yes.
I'm abusing the problem.
So like, is the only place where you need the random order is when you need to know the F2 or?
Good point. Yeah, only F2. Literally everything else I said till whatever assumption and everything was so partially random. Like we still need a heavy hitter to be randomly ordered. That is like at the crux of this algorithm because like I'm assuming that heavy hitter occurs in this like evenly spread way that I'm able to detect it in a nice manner. But if it's like if all the heavy hitters are concentrated somewhere, I don't know. I mean, of course I know how to do it. If I'm promised it, it's going to be concentrated somewhere. But the point is like, how do we design an algorithm somehow that takes care of everything? We don't know yet. Yeah. Our algorithm only works when heavy hitters spread. Yeah.
Right.
Do you have a sense of like how much randomness is being used and what sort of bounds you get if you include the random bits in the
Very good question. We use crazy amounts of randomness.
The formal amount?
Yes. The formal amount says that we use crazy amounts of randomness. Yeah, that's a good point. Like we right now really need those sets S1, S2, all that stuff to solve. And we only that those sets give us a sense of what was sampled and what to be checked. If we don't know that, somehow it's hard to avoid using log n space throughout, and somehow we can't boost the success probability after that. So that's a very good question, and it is indeed some sense of caveat that we really need that much amount of randomness, but yeah.
Is the algorithm of the log 1 over delta over n that also is in this like?
No, I don't think they use like they don't need free randomness.
Okay.
Like this, yeah.
I think other question we'll take offline. And then Jane.
Thank you.
Thank you.
Thank you.